second day in Chapter 5, and this time we are differentiating natural log functions a little bit more. We already did this, so I'm going to jump right to problem number 1. If I want to take the derivative of natural log of cosine of x, well, derivative of natural log is 1 over what I'm taking the natural log of, which in this case is cosine of x, times the derivative of what I'm taking the natural log of. Well, the derivative of cosine would be the opposite of sine of x. So if I now put that together, I think that would end up being the opposite of tangent of x. So there's your little bit of a review just to kind of warm us back up for what we're trying to do, because we're going to bring in a new concept today, and that new concept is this thing that we're going to call logarithmic differentiation. Logarithmic differentiation to make derivatives more manageable. I'm looking at problem number 2, and I'm feeling like I know how to do that problem. I've done that kind of thing before. I see the fraction x squared plus 1 over x squared minus 1, and that's inside of a quantity raised to the, or a cube root. So if I wanted to do the derivative, I would have to take the, start off with chain rule, and then when it came time to do the derivative of the inside, I'd have to do quotient rule. And I'm feeling like the simplification, pardon me, is going to be terrible. So here's an alternative to that. Logarithmic differentiation, we're going to try to make logs easier. Okay? Make derivatives easier by using natural log. That's the idea. Okay? We're going to try to make things simpler, and we're going to do this very simply. Logarithmic differentiation says, I'm looking at problem number 2, and you know what would really be nice? I wish I could use my log rules to expand that, much like we did the last problem on yesterday's notes. That would really be nice. It would be nice if I could, and I think I can go back to it, it would really be nice if I could look at, if I could do what I did here in problem number 8 on this problem that I have right here. Well, I can't if there's no log. So what we're going to do is we're going to introduce the log. We're going to take the natural log of both sides. So if I do that, left side of my equation becomes natural log of y. Right side of my equation becomes natural log of this quantity, x squared plus 1. And instead of using the radical, I'm going to use an exponent. That's my personal preference. Because now I'm looking at the right side of that thing, and I'm feeling like, you know what, I could use my log rules. I could make things a heck of a lot easier. How about if we take this right side and let's expand it? Let's make it, well, I could put a 1/3 in front of everything to start with, or maybe I should even do that over here. Let's take this 1/3 and let's put it down in front of everything. So now if I do that, now expand those two logs that are, those two quantities being divided into two separate logs. 1/3 quantity natural log of x squared plus 1 minus natural log of quantity x squared minus 1. Well, now that looks like a lot better thing to take the derivative of, because if I take the derivative of the left side, 1 over y dy over dx equals derivative of the right side. Well, let's see. I know that 1/3 is going to be along for the ride, times the derivative of natural log of x squared plus 1, 1 over x squared plus 1 times 2x, minus net derivative of natural log of x squared minus 1, 1 over x squared minus 1 times 2x. So there's my derivative. Well, now if I start cleaning it up, looks like 1 over y dy over dx is equal to 1/3 times the quantity 2x over x squared plus 1 minus 2x over x squared minus 1. And what I've done, as it says up there, is I made my derivative easier by introducing a natural log. I didn't have a natural log. Once I do, I can change it around. I can make things a little easier on myself. But now we better make sure that we finish the problem. Well, if we're going to go and finish this problem, the first thing I'm probably going to need is a little bit more space. So let's see. If I want to get dy dx by itself, the first thing I'm going to need to do is I'm going to need to multiply by y. So my dy over my dx is going to be 1/3. And I'm just going to write y right there for right now. And then if we go to get a common denominator, let's see, we'd have to multiply, common denominator would be x squared plus 1 times x squared minus 1. And let's see. So the first quantity I'd have to multiply by x squared minus 1 on the top and on the bottom. And the second quantity I'd have to multiply by x squared plus 1 on both the top and on the bottom. If I do that, I think those 2x cubes are going to drop out. And I think after distributing my negative, I'm going to end up with a negative 4x right there in that numerator. And then the only thing I have left to do, since I know what y is equal to, I'm going to go back and I'm going to rewrite that y is the same thing as that cubed root of x squared plus 1 over x squared minus 1. Let's put that in its place. So in place of y, I'm writing cubed root of x squared plus 1 over x squared minus 1. And then I'm multiplying that by the quantity negative 4x over x squared plus 1 quantity times x squared minus 1 quantity. So this, after we're done with all of that mess that we just made, would be our derivative of that function. And the idea then would be, I had a nasty derivative. I would have had terrible simplification. Here's a case where I have fewer rules to keep track of. It's a little more straightforward. And that's an example of logarithmic differentiation. Problem number 3 isn't so much logarithmic differentiation as much as it's just a big pain in your butt. Because we've got some nasty stuff going on here. So we've got to find our derivative, but this time everything's defined implicitly. I'm looking at it. I see 3 different y's. I think I'm going to have trouble isolating that y. So if that's the case, then let's go ahead and let's do, let's kind of take the derivative if we can. Now, one of the things that I might do is I would probably start this problem by saying that natural log of xy is the same thing as natural log of x plus natural log of y. Now, that's just my preference, but I'm looking at it thinking I would like that better. Plus my x squared y is equal to xy plus 6x. So let's start taking derivatives. So my derivative, let's use a different color. Derivative of natural log of x would be 1 over x multiplied by a 1. Plus derivative of natural log of y. Now this is defined implicitly, so 1 over y times dy over dx. Plus derivative of x squared y, that's going to be a product rule. X squared times dy over dx. Plus y being multiplied by the derivative of x squared, which would be 2x. Equals xy, there's another product rule, x dy over dx. Plus y times the derivative of x, which is 1. Plus a 6. So there are 1, 2, 3, 4, 5, 6, 7 terms, 3 of whom have dy over dx's. So I'm going to take this one and move it to this side. I'm going to take this one and move it to that side. I'm going to take this one and move it to that side. Combine some steps here. So let's see. On the left side, I've got a dy over a dx that's being multiplied by the quantity 1 over y plus x squared minus an x. And on the other side of my equation, I already had a y plus 6. And let's see, I subtracted a 2xy. And I also subtracted a 1 over x. So now in order to get dy dx by itself, let's see. So that dy over dx would be the same thing as y plus 6 minus 2xy minus 1 over x over 1 over y plus x squared minus x. Now, everybody knows that there's 2 issues here. First off, they're never going to give you a standardized test answer or anything like that, nor anywhere else that's got fractions inside of fractions. So let's make a real quick multiplication here of xy on the top and on the bottom and clean it up. And if I clean it up, I think we'll end up with a result here of my derivative being x times y squared plus 6xy minus 2x squared y squared minus x's cancel y over the top of x plus x cubed y minus x squared y. And if I double check that really quick to make sure I know what I'm doing, it looks like we got that thing right. So here After all of that nastiness is an implicitly done derivative using logs. So a lot of nastiness, a lot of yuckiness here, but they also can be a lot worse. So there we go. There's second day, chapter 5.